for a transparent, here observe transparent, or of course it is also called as the diathermanous body. Diathermanous body. He has given alpha value is how much, reflectivity is how much, and the transmissibility is how much. Here he has directly mentioned this is a transparent body. Transparent is nothing but like a glass we can see. So whenever the incident Q will be falling on the transparent body, for a transparent body, what happened? It cannot be reflected. Remember, it cannot be reflected. It cannot be absorbed. Then what happened is nothing but whatever the total incident rays will be going to be transmitted with through the transparent body. So tau is equals to, here tau is equals to 1, alpha is equals to 0, rho is equals to 0, where rho is nothing but reflectivity and alpha is nothing but absorptivity and tau is nothing but transmissibility. Here look at the answer. Tau is equals to 1 and rho and alpha will be 0. This is the solution. Okay. Emissivity of a black body is equals to, here emissivity we are generally showing as epsilon. What is emissivity is nothing but it is the ratio of emissive power of a body to the emissive power of a black body. Generally, emissive power of a body to the emissive power of a black body. General thing is emissive power is nothing but transmissibility. Whatever the transferred energy, that is generally emissive power of a black body is equal to, we are generally taking as 1. We are taking the emissive power of a black body equal to 1. Emissivity or emissive power, emissive power is nothing, emissivity is nothing but emissive power of a body to the emissive power of a black body we are generally taking, and this is in the equal to 1 for the black body because of the transmissibility is equal to 1, absorptivity is equal to 0, reflectivity is equal to 0. So generally we are taking the emissivity of a black body is the emissive 1, means this one, because of transmissibility is equal to 1, because generally whatever the emissive power is nothing but transmissible power, that's it. As the coefficient of transmission of a perfectly black body is equal to, coefficient of transmission here 1, coefficient of transmission of a perfectly black body is equal to 1. What is the correct formula for the Biot number? Here you need to understand what is some dimensionless numbers, like Fourier number, Nusselt number, Biot number, Reynolds number. So all these are dimensionless number. Dimensionless is nothing but which doesn't have any units. So if you are look at this one here, Biot number is the HL by, of course here alpha he has shown the alpha, but K you can take it as K, thermal conductivity, conductive heat transfer in solid. General Biot number is nothing but convective heat transfer to the conductive heat transfer. But both are not the solids or both are not the fluids. Here if you look at the convective heat transfer, generally we are taking in terms of fluids, but conduction in terms of solids. That is the difference. And here if you are looking at this one, Nusselt number, there is the same thing, convective to the conductive. Here also convective to the conductive. But here if you are looking at this one, observe this one at this position. Here this is also HL by K. Here this is also HL by K. But if you are observing, it is K or lambda. This is for solid, but this is as fluid. That is the difference. HL by K. This is also HL by K. And a Fourier number, Grashof number, Prandtl number, Reynolds number. We need to understand these things. Biot number is the convective heat transfer in the fluid to the conductive heat transfer in the solid. Whereas Fourier number is the diffusive transport rate to the storage rate. Grashof number is the buoyancy force to the viscous force. And Nusselt number is the convective heat transfer in the fluid to the conductive heat transfer in the fluid. Prandtl number, this is Prandtl number, viscous diffusion rate to the thermal diffusion rate, means thermal diffusivity. Okay. Reynolds number is nothing but inertia force to the viscous force, that is rho VL by mu. Generally we are writing rho VL by mu like that. See here, C is nothing but velocity generally. Okay, rho of the fluid, c is nothing but velocity, L is nothing but length, mu is nothing but viscosity. So if you are looking at that, HL by K, this is the answer. But if you are observing, there might be giving like that also. HL by K solid he may give like this, and another thing is HL by K fluid he may give, where H is the convective heat transfer coefficient, convective heat transfer coefficient, and K is the thermal conductivity, where L is the length. If you are giving like this, HL by K only, but K is for the solid, K is for the fluid, we need to go for the K for the solid. Why? Because Biot number is nothing but, if you are looking at this one, Biot number is the conductive heat transfer of the fluid, that is convective heat transfer. What is convective heat transfer? We'll see. For this one, I am just writing the how it will be. Okay. Convective heat transfer, generally HA Ts minus T infinity. Convective heat transfer. Conductive heat transfer means Ka delta T by dx. Generally AA will be going to cancel dt, or Ts minus Ta will be going to cancel. This dx I am taking to the power top side. So you can write down that H into dx. Instead of writing dx, I am taking the length HL by the K as it is. But here this is the solids. This is happening in the solids. So we are taking as solids. So we are going to get the HL by K solid. Similarly here also the same thing. Convective to the conductive same. But here we are taking the fluids. That is the main difference. Nusselt number as well as the Biot number. So HL by K solid here, remember. Even he mentioned or doesn't mention HL by K solid, you need to remember. Whereas Nusselt number is nothing but HL by K fluid. Remember this one. Okay. And Reynolds number is nothing but rho V L by mu. Rho V dr. Anything. Rho V L by mu or rho V D. Rho V D by mu. Whereas D is in the terms of cylinders, like that we are going to take D diameters, whereas L is nothing but the length, mu is the viscosity, rho is the mass density, V is the velocity. All these things we are going to get. For effective working of the fins, the thickness of the fins must be. For effective, we have already seen this is the engine. Suppose I am going to add some fins. For effectiveness, what the thickness of the fin? What is the thickness of the fin is nothing but very small. Because if we are taking the very large size fin or very large thickness, if you are going to take the very large thickness like this, if I am going to take like this, then what happened? This area will be going to be increases. This area will be going to be increases. What happened if the area is increasing at the same time? What is the area of the convective? Suppose I am taking, instead of like this, I am taking 3 at the same place. I am taking the 3 fins. If I am taking in the same gap, I am taking 3 fins. What happened? Because area will be here, this area, 3 areas. But here only one area will be coming into picture. So the area will be shortaging in the convective heat transfer also. Whenever the area is reducing the convective heat transfer, what happened? Q will be reducing. So fins are used in order to increase the heat transfer. Whenever the thickness, generally, just a minute, I will show you another concept like this. This is one fin, suppose. But instead of like this, I am taking another fins like this. This is one fin. This is another fin. This is another fin. Likewise, I have taken with the same length, I have taken 3 fins. Here area, if you are observing area, what happened? This area, this area, this area. There are 3 areas, top and bottom, top and bottom, top and bottom. But here if you are looking at only 2 areas, means like this. If you are adding this 2, there will be 2 areas are missing, our palms. Yes or no? thickness, whenever I am increasing the thickness, only top and bottom, only two areas will be coming into picture. Whereas I am just keeping some distance. There are two fins I am making. These two palms are also coming into picture. So the area will be increasing. So area is increasing whenever the thickness is very short. Okay, thickness is very small. So what happened? Thickness is very small. The convective heat transfer area will be increases. Whenever the convective heat transfer area will be increases, convective heat transfer will be increases. Whenever the convective heat transfer will be increases, our goal is reached. So we need to keep the fins thickness is very small, very small. Radiosity is the sum of the radiation. The thing is emitted, reflected, absorbed, no. Emitted, reflected, transmitted, no. Emitted, transmitted, reflected, absorbed. What is radiosity? Radiosity generally, suppose this is the body and there is Q is the, or G, whatever the name we call it as, G is the incident energy. Then there are three possibilities. One is transmitted, one is absorbed, and another one is reflected. So whatever the total radiation leaving from the surface is known as radiosity. Generally, whatever the total or sum of energy leaving from the surface, energy leaving, leaving from the surface, whatever the total energy leaving from the surface is known as radiation. Now whatever the total, one is absorbed, it is not leaving, so absorbed is correct, not correct. One is emitted, reflected and transmitted. Emitted, okay fine. Reflected, okay fine. Transmitted, okay fine. Emitted, reflected, transmitted, but not absorbed. Remember, absorbed is not the correct. Emitted, reflected as well as transmitted. So this is the answer, emitted, reflected and transmitted. Whatever the total radiation or total sum of energy, radiation energy. Here I am taking the radiation energy leaving. One is emitted, means coming out, and reflected, of course reflection, and transmitted. The total will be the sum. Radiosity is nothing but the summation of the emitted sum of radiation emitted, reflected as well as transmitted. The total radiation leaving a surface per unit time per unit surface area. The total radiation leaving a surface per unit time as well as unit surface area is nothing but radiosity is nothing but it is the total energy leaving. But here, what here? Leaving, observe, leaving a surface per unit time. So generally leaving is nothing but radiosity. Incident is nothing but irradiation. Incident is nothing but irradiation. Radiosity is nothing but per leaving. What is the ratio of the buoyancy force to the viscous force? Generally we have seen here buoyancy force to the viscous force. Buoyancy force to the viscous force is nothing but Grashof number. So remember that Grashof number. This is the solution. What is Nusselt number? HL by K fluid, because convective heat transfer to the conductive heat transfer in this is for solid, fluid to the fluid, fluid to the fluid. Whereas Prandtl number is also, Prandtl number is nothing but, look at this one, Prandtl number is nothing but Prandtl number, viscous diffusion rate to the thermal diffusion, viscous force to the thermal diffusivity, alpha, that is we are generally writing. Reynolds number is nothing but, Reynolds number is nothing but inertia force to the viscous force is nothing but Reynolds number. Just remember all these things, numbers, okay. Yes, so the solution is Grashof number. Prandtl number, you know that. Reynolds number, you know that. Prandtl number is nothing but diffusion to the thermal diffusion. Whereas Reynolds number is nothing but rho VL by mu. Rho VL by mu. You need to remember the formulas also. If the Reynolds number is less than 4000, less than 2000, it is laminar flow. The flow is laminar. And greater than 4000, it is turbulent. Generally, what is the relation between the absorptivity, reflectivity and transmissibility of a grey body? Here remember that grey body he has given. There are two bodies. One is black body, another one is grey body. Grey body. What is these things? Means both are opposite. Here for the black body, what happened? Absorptivity is rho is equals to 0, tau is equals to 0, alpha is equals to 1 generally. But for the grey body, opposite. Rho is equals to rho plus tau is equals to 1, whereas alpha is equals to 0. Means there is no absorption. There is no absorption. Only transmission or reflection. So here if you are looking at this one, rho plus tau is equals to 1. This is the for the grey body. For the grey body, it is opposite. Generally, these two are opposite. For this one, rho is equals to 1, alpha is equals to 1, rho and tau is equals to 0. For this one, alpha is equals to 0, rho plus tau is equals to 1. General thing is for any body, rho plus tau plus alpha is equals to 1. How it is coming is nothing but, suppose I am taking Q naught is the incident energy on a body, and sum of energy will be, suppose QR or QA is the absorption, QT is the transmissible, and QR will be reflection. Suppose I am taking. How can I write that? Nothing but Q naught is equals to, I can write down Q naught is equals to QR plus QA plus QT. Generally we can write down like this. And of course I can also write down that I am just taking this to this side. What happened? 1 is equals to QR by Q naught plus QA by Q naught plus QT by Q naught, where QR by Q naught is equals to rho, QA by Q naught is equals to alpha, and this one will be tau, simply. And that is the part of the radiation. The radiation is a part of the total incident. One of the part of the absorption is the total, one of the part of the total incident. Transmission is energy is also part of the total radiation. So for the grey body, alpha plus tau is equals to 1. Alpha plus tau is rho plus tau is equals to 1, because alpha is equals to 0, alpha is equals to 0, alpha is equals to 0. These three are not the correct. Only this one is the answer. Prandtl number is the ratio of, generally we have seen the Prandtl number is nothing but generally diffusivity comes in the denominator. There are two things. Here if you are looking at that Prandtl number is nothing but viscous diffusion rate to the thermal diffusion. Viscous diffusivity means viscosity, absolute viscosity to the thermal diffusivity. Generally mu by rho, alpha is equals to 1 by alpha is equals to mu by rho Cp. We can write down, general thing is, or you can write down alpha is equals to rho Cp by mu. Okay, okay, fine, nothing to worry. Okay, absolute viscosity to the thermal diffusivity is nothing but the Prandtl number. General diffusivity, thermal diffusivity will be in the denominator, and the absolute viscosity to the thermal diffusivity. Okay, mu by alpha. Stephen Boltzmann. Yes, generally we have seen the conduction equation. That is, conduction equation will be Fourier's equation. Fourier's equation, that is Q is equals to Ka dt by dx, whereas convection heat transfer is equals to HA, Q is equals to HA delta T, Ts minus T infinity or del. Similarly, this is Newton's law of cooling. Newton's law of cooling. Similarly, for the radiation also one equation will be present, that is Stephen Boltzmann's equation. That is Stephen Boltzmann equation. According to this one, Q is equals to sigma into A into T power 4. Sigma into A into T power 4. Okay. where sigma is the Stephen-Boltzmann constant, which is equals to 5.67 into 10 to the power of minus 8 watt per meter square Kelvin power 4. Watt per meter square Kelvin power 4. This is the Stephen-Boltzmann constant. Remember this value also, 5.67 into 10 to the power of minus 8 watt per meter square Kelvin power 4. A phase change heat exchanger. Heat exchangers, generally I have given one diagram. As this is there are two heat exchangers. One is parallel flow heat exchanger, another one is counter flow heat exchanger, or co-current and counter current. Of course, this is parallel flow. If you are looking at this one, this is the flow direction of the fluid, hot fluid, and this is the flow direction of the cold fluid. Similarly, this is the graph. And similarly, if you are observing here, this is the flow direction of the hot fluid and this is the flow direction of the cold fluid. What happened? Suppose I am taking this is the inside, this is the inside of the cold fluid. Means here the cold fluid is entering, here the hot fluid is entering. Both are entering and both are living at the outside. Here this is the inlet, I am taking this is the inlet, and here this is the outlet. Okay. For this, what happened? The temperature of the cold fluid will be going to be increases because of course not the direct contact but indirect contact. Cold fluid temperature is increasing, hot fluid temperature will be going to be decreases. Similarly here also, that hot fluid temperature is going to be decreasing and cold fluid temperature is going to be increases. Okay, but coming to here also the cold fluid temperature is increasing. Cold fluid temperature is increasing, hot fluid temperature is decreasing. But if you are looking at the hot fluid is coming from here and the cold fluid is coming from another end because of counter flow. Because of counter flow, the direction will be changing. So hot fluid is entering here, cold fluid is entering here. If you are observing, hot fluid temperature is going to be reducing, but cold fluid temperature is increasing, the same, but both are in opposite direction. Here the both are in same direction. Then what is happening is nothing but, if you are looking at what happened, LMTD, he is asking the phase change. Phase change is nothing but the temperature is not going to the phase is not going to be changing. The phase is not going to be changing in the heat exchanger. Then how it will be is nothing but for a phase is not changing is nothing but, suppose this is the one phase, only temperature is varying. There are two things, only one temperature is changing, so phase is not changing. But here he is asking the phase change. For a phase change heat exchanger, generally LMTD, according to LMTD technique, we are going to write down that delta T1 minus delta T2 or delta T1 minus delta T2 by ln delta T1 by delta T2. Generally we are writing like this. Okay, if you are looking at that, what is delta T1, what is delta T2, and this is means whatever the temperature difference, TH inside, TL, TC in here, TH in here and TC in here, this is the delta T1, means the temperature changes, and this is the TH out and TC out, and this is the delta T2. If you are looking at that if you are writing that, this is the delta Tm, this is the delta Tm. Generally you are writing Q is equal to UA delta Tm or HA delta Tm. U is nothing but overall heat transfer, where delta Tm is equal to delta T1 minus delta T2 by ln delta T1 by delta T2. What happened is, in the sense is nothing but, whenever Q is constant, A is constant, generally flow heat exchangers in the heat exchanger, which depends upon delta Tm only. But for the counter flow or parallel flow, here only counter flow, parallel flow, and one more flow is also there, that is cross flow. We are not going to consider that one, only this one. For this one, if you are looking at this one, if you for the phase change, if I am going to draw for the phase change, how the phase change will be is nothing but the same thing. Only instead of changing the temperature, if the phase is changing, means the same hot fluid is same, but coming to the cold fluid like this. Similarly, in the this is the parallel flow. This is a parallel flow. Coming to the counter flow. This is a counter flow. Generally, observe. Sorry. This is a counter flow. This is the counter flow. Means the phase is changing. Here delta T1 is this one, delta T2 is this one. Here also delta T1 is this one, delta T2 is this one. Generally in the parallel flow, in the counter flow, I will redraw again. Just a minute. You will understand. Yes. Here delta T1, this one. Delta T2 is this one. Here also delta T1 is this one, delta T2 is this one. One is counter flow and another one is parallel flow. Which one is counter flow is nothing but this is parallel flow, this is counter flow. Then how you are going to tell is nothing but the direction. With the direction only you can tell the whether the parallel flow or counter flow. Phase is nothing but the phase, then means there is no change in temperature. Here also there is no change in temperature. Temperature is not going to change, means the phase is going to change. If this is the phase change, then where you are going to get is nothing but the condensers or heat exchangers. Okay. And here what happened is nothing but the delta T1 is equal in the counter flow, which is equals to delta T1 in the parallel flow. Similarly, delta T1 in the delta T2 in the counter flow is equals to delta T1 T2 in the parallel flow. So from this you can write down that delta T1 is same, delta T2 is same, here also same, here also same. So delta Tm is not going to change. So whenever the delta Tm is not going to change, Q is also not going to change. Means whether you are taking the counter flow or parallel flow, LMTD, according to the LMTD technique, delta Tm value will be same for counter flow as well as parallel flow. So whenever the delta Tm value will be same, so for the same inlet and exit temperatures of the flow fluid, the LMTD of the counter flow is always greater than the LMTD for parallel flow. Here LMTD for the counter flow is always equal to the LMTD for parallel flow in the phase exchanger. But general thing is LMTD for the for equation exit temperatures of two fluids, for the same exit temperatures of the fluid, the LMTD for counter flow is always greater than the LMTD for parallel flow. For the same heat transfer Q, same overall heat transfer coefficient U naught, surface area required for parallel flow operation is always. Here he is asking for the same heat transfer, Q is same, for same U naught, surface area required for parallel flow is always more than. Answer is more than. The area required for the parallel flow is always required more for the comparatively counter flow. For the comparatively counter flow, area is requiring more in the parallel flow. Generally, a heat exchanger with heat transfer surface area same, overall heat transfer U same, handles two fluids, heat capacity C max as well as C minimum. Okay, fine. The parameter NTU used NTU. There are two methods: NTU method, LMTD technique. There are two methods: NTU method as well as LMTD technique. Till now we have seen the NTU method. Now, till now we have seen the LMTD technique. Now it is the NTU method. In the NTU method, what is NTU? He is asking about what is NTU. Answer is AU by C minimum. AU by C minimum. We will call it as NTU as AU by C minimum. We will call it as NTU. AU by C minimum. The equation of the effectiveness effectiveness of the heat exchanger 1 minus e power minus NTU for a heat exchanger is valid in case of. Generally, we want to write down. I am going to write down some equations regarding this one for the parallel flow as well as counter flow. Generally, just I am writing down. Here I am writing the general equation is epsilon is equals to 1 minus e power minus NTU of 1 plus C by 1 plus 1 minus e power minus NTU. 1 minus e power minus NTU by 1. this is the general equation is 1 minus e power minus NTU of 1 plus c by 1 minus c into e power 1 minus c into e power minus NT of 1 plus c. This is a generalized equation. 1 minus here c, where c is the c minimum to the c maximum. Okay, c minimum to the c maximum, we'll call it as, c minimum to the c maximum is called c, this c. N2u is the nothing but ua by c minimum or au by c minimum generally, and 1 minus e power minus NTU of 1 plus c by 1 minus e power c by c into e power minus NTU by 1 plus c. This is a generalized equation, but he is asking, what he is asking, effectiveness is equal to 1 minus e power minus NTU for heat exchange is valid. Only 1 minus e power minus NTU he has given. That means here c value should be is equal to 0. C value should be is equal to 0. When it is going to be 0, generally we need to understand. When it is going to be 0 is nothing but for the phase change. For the phase change heat transfer. For the phase change heat transfer, C value is 0. In which mode we are going to take this C value is 0, means the phase change. Boiler and condenser for the parallel flow, boiler for the condenser for the counter flow, boiler and condenser for both the parallel and counter flows, gas turbine for both the parallel. First of all, gas turbine, what happened in the gas turbines and what happened in the boiler and condensers, we need to understand. Boilers or condensers is nothing but generally for phase change only. Boilers aina, that means boilers, condensers, we are generally condensers, or boilers, condensers, we are taking as the phase change. Absolutely correct. Phase change. Whereas gas turbines is nothing but there is no phase change. This is the power producing. So absolutely this is not the correct. Absolutely this is not the correct. Then what happened? 1 minus e power minus NT. Whether it is for the counter flow or 1 minus e power minus NTU. Here 1 minus e power minus NTU. Whether it is counter flow or parallel flow, we need to understand. Whether it is counter flow or parallel flow, remember both are same for the phase change. Just now we have seen phase change. For the phase change, C value is 0. So we can write down that epsilon is equal to 1 minus e power minus NTU. Whether it is parallel or counter. So both these three are correct. Parallel, if it is coming into picture, general, just observe. Just this is a generalized equation. If you are keeping the C value 0, epsilon will be 1 minus e power minus NTU only. E power minus, this is applicable for the both parallel as well as counter flows. Okay. So this is the solution. C value is the solution. Because both are because of both. What is the effect of the convective heat transfer coefficient H on the fin effectiveness? S. Here he has given that what is the effect of convective heat transfer, means Q is equal to Q convective is equal to HA delta T, Ts minus T infinity, Ts minus T infinity. Fin is effective. Effective if the value of the convective heat transfer coefficient is small. Fin is effective if the value of convective heat transfer coefficient is large. When it is will be fin is effective is nothing but we need to keep the fins in order to increase the heat transfer. In order to increase the heat transfer, we are going to keep the fins. When the H value is more, this one will be more. Yes or no? So if the fin is effective, if the value of convective heat transfer coefficient is large only. Yes or no? Because H value is more, convective heat transfer is more. So the answer is B value. Fin is effective doesn't know. Generally H value, if you are taking a more H value material, then if the H value is more, convective heat transfer is more. Consider the heat is transferred through a wall of surface A, thickness A, and the rate Q. At the rate Q, what is the thermal resistance? Here thermal resistance. there is a concept called thermal resistance. We are generally writing Q is equals to Ka dt by dx. Sorry. And there is an electrical analogy is there. Thermal resistance is nothing but he is asking that R value means if you are writing the thermal if you are writing that electrical analogy, delta V is equals to I into R. Thermal, we just changing this equation in terms of this one. If I am going to write down in terms of this one, I can write down that delta T is equals to or dt is equals to Q into here I am writing L instead of writing the dx I am writing L. So Q into I am taking this one, L I am taking this type. So by K into A. Just delta T is equals to Q into L by Ka. Here delta T, delta V and Qi. R is equals to I can write down that L by Ka. L by Ka. So answer is L or thickness T by Ka. Here dx instead of so T by Ka. Thickness is here. He has given the thickness is T. Thickness as T. So instead of writing the dx I am writing the thickness as T. So here thickness as T. Here I am writing the thickness as T. So here T will be comes in the picture. So T. If you are observing this and this, you will get delta V instead of delta V, delta T, I, Q. So R. R is nothing but the resistance. So here this is the resistance. T by Ka is the resistance. The same thing. So T by Ka. Which one is true for the opaque body? Opaque. Generally, opaque body is nothing but in the radiation we are going to get the opaque bodies. What is opaque body is nothing but we have seen the black body, grey body and one is opaque body. Black body. For the black body, what happened for the black body? Black body, alpha is equals to 1, rho is equals to tau is equals to 0. For the grey body, alpha plus grey body only alpha is equals to 0, rho plus tau is equals to 1. Whereas for the opaque body, opaque is nothing but tau is equals to 1, tau is equals to 0, sorry, alpha plus rho is equals to 1. Only either absorptivity or reflector, but it cannot be transmitted like wooden, it cannot be transmitted. So answer is tau is equals to 0 means transmissibility is equals to 0. Transmissibility is equals to 0. Okay, that's it. Thank you.